Welcome to our session on vector error correction models, or VECMs. This presentation will cover the theory, specification, and practical estimation of these powerful time series models in EViews. Our session goal is to master the transition from short-run noise to long-run equilibrium. A key concept we'll explore is cointegration, which is the statistical implication of the existence of a long-run economic relationship. The first major challenge is that many macroeconomic variables, like GDP or prices, are non-stationary. They have a unit root, meaning they tend to trend over time and don't revert to a constant mean. We denote this as being integrated of order 1, or I1. If we ignore this and regress one I1 variable on another, we risk falling into the trap of spurious regression. This is where we find a high R-squared and seemingly significant t-statistics, but the relationship is entirely meaningless and driven by shared trends, not a true economic connection. The solution is cointegration. If two or more non-stationary variables share a common stochastic trend, a linear combination of them can be stationary. This stationary combination represents the long-run equilibrium, and a VECM is the perfect tool to model this. Stationarity is rare in macroeconomics, as most variables exhibit growth. VECMs allow us to model this growth and the underlying long-run relationships without violating statistical laws. The first step is always to test for unit roots using tests like the ADF, or Augmented Dickey-Fuller, or Phillips-Perrin test. We need to determine if our variables are stationary, I0, or non-stationary, I1. If all variables are stationary at levels, I0, we can proceed with a standard VAR, or vector autoregression, model and levels. If the variables are non-stationary, I1, we must then test for cointegration using the Johansen test. This test is the crucial gatekeeper for using a VCEM. Based on the Johansen test results, if we find cointegration, we must use a VCEM. If there is no cointegration, we must use a VAR model on the first differences of the variables to achieve stationarity. A standard VAR model focuses exclusively on short-run dynamics. It models each variable as a function of its own past values and the past values of other variables in the system. Crucially, a standard VAR assumes no long-run equilibrium constraint. It's best used for forecasting when variables are stationary or when they are non-stationary but not cointegrated. A VECM, on the other hand, is more sophisticated. It models both the long-run equilibrium and the short-run adjustment towards that equilibrium. The model explicitly restricts variables to converge to their shared long-run relationship. The key advantage of a VECM is its ability to distinguish between permanent shocks, which affect the long-run trend, and transitory shocks, which cause temporary deviations from it. The analogy of a drunk man and his dog is perfect. A VAR model is like tracking the drunk man alone. His path is a random walk. A VECM is like tracking the man walking his dog on a leash. Both wander randomly, short-run dynamics, but the leash, the cointegrating relationship, ensures they never get too far apart, long-run equilibrium. This slide presents the core mathematical equation of a vector error correction model. The left side, delta YT, represents the short-run changes in our variables, which are expected to be stationary. The first crucial term on the right, pi yt-1, is the error correction term. This term is the heart of the VECM, encapsulating the long-run information. The Math Check section highlights the magic of VECM. This entire term, pi yt-1, is stationary, even though yt-1 itself is non-stationary. This stationarity balances the equation, a fundamental principle derived from the Granger representation theorem. The second part of the equation, the summation of gamma I delta yt minus I, captures the short-run dynamic adjustments, showing how past changes influence current adjustments. Below the main equation, we see the rank condition for the pi matrix, where pi equals alpha beta prime. If the rank of pi is R, it indicates that R cointegrating vectors exist, defining the number of distinct long-run relationships among the variables. This slide breaks down the economic meaning of the key coefficients in a vector error correction model. First, we have the beta vector, or the cointegrating vector. This vector defines the long-run equilibrium relationship itself. It gives us the parameters of the long-run equation, such as GDP equals beta 1 times M1 plus beta 2 times interest rate. Second, we have the alpha coefficient, also known as the adjustment coefficient. This coefficient measures the speed at which a variable returns to its long-run equilibrium after a shock. It tells us what percentage of the previous period's disequilibrium is corrected in the current period. For the system to be stable and converge back to equilibrium, the alpha coefficient for an endogenous variable must be negative. A positive alpha would mean the variable moves further away from equilibrium, causing the system to explode. An alpha of 0 means the variable is weakly exogenous and does not respond to deviations from equilibrium. This slide outlines the critical assumptions and requirements for effectively using a vector error correction model. First, all variables must be integrated of order 1, or I1. This means they are non-stationary in their levels, but become stationary after taking their first difference. Second, there must be statistical evidence of cointegration. The Johansen test must indicate at least one cointegrating vector, meaning the rank R must be greater than or equal to 1. This confirms the existence of a long-run equilibrium relationship. Third, we need to determine the appropriate lag length, denoted as P, for the underlying unrestricted VAR model. This is crucial to ensure the model's errors are white noise. The number of lags in the VECM will then be P-1. Finally, we must specify the deterministic trends, such as intercepts and linear trends, for the Johansen test. There are 5 different cases, and selecting the correct one is vital for robust results. As a pre-estimation step, it is imperative to always determine the lag order P on the unrestricted VAR before running the Johansen test. This ensures that the dynamic specification is correct, and consequently, the VECM lags will be P-1. This slide illustrates how to access the vector autoregression, or VAR, estimation in EViews, which is the foundational model for a vector error correction model. On the left, we see the EViews navigation hierarchy. To estimate a VAR, you typically go to the Quick menu on the main EViews toolbar and then select Estimate VAR. This is highlighted as the access point. It's important to note that EViews treats VECMs as a specific restriction of a VAR. Therefore, you won't find a separate top-level Estimate VECM menu directly. You first estimate a VAR and then impose the cointegration restrictions to form a VECM. On the right, there are alternative tips for initiating a VAR. You can also select your group of variables in the work file window, then right-click and choose Open as VAR. Additionally, for those who prefer the command line, simply typing VAR followed by your variable names will open a VAR specification dialog, as VAR is considered the base object. This slide shows the VAR specification dialog in EViews, configured for a vector error correction model, VECM. Crucially, when specifying lag intervals for endogenous variables in a VECM, you must enter the lags of the differences. For example, if your underlying VAR model has a lag of P, then in this dialog for a VECM, you should enter 1 P-1. This is a common syntax trap because EViews VECM lag specifications refer to the first differences, not the levels of the variables. So a 1-2 entry in the VECM dialog actually implies lags 1, 2, and 3 in the original levels VAR model. Always remember to adjust your lag input accordingly to ensure correct model specification. We begin our case study with U.S. macroeconomic data. The crucial first step in any time series analysis is data inspection and unit root testing. On the right, you can see our workflow. First, load the data. Second, apply log transformations if necessary to stabilize variance. Third, run an augmented Dickey-Fuller ADF test for unit roots. And finally, proceed only if all variables are found to be integrated of order 1, or I1. The table on the left shows a snippet of our data, including GDP, M1 money supply, and TB3, Treasury bill rates. The graph visually confirms that these variables exhibit clear trends. Most importantly, the ADF test results, prominently displayed at the bottom, confirm that GDP, M1, and TB3 are all I1. This means they are known stationary in their levels, but become stationary after first differencing, which is a key prerequisite for vector error correction models. Based on the unrestricted cointegration rank test, we found one cointegrating vector. Therefore, we set the rank equal to 1 in the VECM estimation settings. Additionally, since the optimal VAR lag was 4, we use a lag of 3 for the VECM, as it is p-1. This slide provides an overview of how to read the EViews VECM output. The output is typically divided into two main parts. The top section, labeled Part 1, Cointegrating EQ, represents the long-run equilibrium relationship, defined by the beta coefficients. This is essentially the static equilibrium target of the system. The bottom section, labeled Part 2, Error Correction Short-Run Dynamics, contains the alpha and gamma coefficients. The alpha coefficients represent the dynamic adjustment speeds, indicating how quickly variables return to the long-run equilibrium after a shock. It's important to remember that standard errors in the output are typically presented in parentheses, while t-statistics are in square brackets. This distinction is crucial for correctly assessing the statistical significance of the coefficients. When interpreting the cointegrating vector from EViews, there's a crucial step involving normalization. EViews presents the cointegrating equation normalized on one variable, here log GDP, and sets everything equal to 0. The output shows log GDP with a coefficient of 1.000, log M1 with negative 0.55, and TB3 with negative 0.02. This translates to the equation log GDP minus 0.55 log M1 minus 0.02 TB3 equals 0. To make this economically intuitive, we rearrange the equation to express our normalized variable in terms of the others. This involves moving the other terms to the right-hand side, which reverses their signs. The final, interpretable long-run equilibrium equation is log GDP equals 0.55 log M1 plus 0.02 TB3. This shows a positive long-run relationship between GDP and both money supply and interest rates. The rule is to reverse the signs displayed in the output when interpreting the impact, as highlighted by the sign reversal due to normalization note. Here, we focus on interpreting the alpha coefficient, which represents the speed of adjustment towards the long-run equilibrium. Looking at the error correction section, under the d.log GDP column, the coefficient for coin-EQ1 is negative 0.15. This is our alpha coefficient for GDP. A crucial sanity check for any alpha coefficient is its sign. It must be negative for the system to be stable and to converge back to the long-run equilibrium. Our alpha of negative 0.15 satisfies this condition. The magnitude of negative 0.15 indicates that 15% of any disequilibrium or deviation from the long-run relationship in the previous period is corrected by GDP in the current period. For instance, if GDP was 1% above its long-run equilibrium last quarter, it will adjust downwards by 0.15% this quarter to move back towards that equilibrium. The associated t-statistic of negative 3.45, which is significant, confirms that this adjustment is statistically meaningful. If alpha were positive, it would mean the variable is moving further away from equilibrium, leading to an unstable and diverging model. If alpha were 0, it would imply that the variable does not respond to deviations from the long-run target and is considered weakly exogenous within the cointegrating relationship. A crucial diagnostic is to test for serial correlation in the residuals. The portmanteau test checks the null hypothesis of no serial correlation. High p-values, example greater than 0.10, for the Q statistics, as shown here, are good news. It means our residuals behave like white noise, and our model's dynamic structure is well specified. For instance, the p-value for lag 5 is 0.205. Since this is much larger than 0.05, we fail to reject the null hypothesis and conclude there is no significant serial correlation up to 5 lags. Visually inspecting a plot of the residuals is also important. We are looking for a random pattern centered around 0, with no obvious trends, cycles, or changes in variance. The plot here shows clean residuals, which further supports our model. If the diagnostic tests fail and you find serial correlation, the most common solution is to increase the lag length in the model. This gives the model more flexibility to capture the short-run dynamics. Other potential issues could be outliers, structural breaks, or an incorrect specification of the deterministic trends. Impulse response functions, or IRFs, are a powerful tool for analyzing dynamic models. They help us understand how variables respond to unexpected shocks over time, allowing us to tell a clear economic story. We can investigate crucial questions, such as, does a variable initially overshoot its new equilibrium? Does it recover slowly? Or does it adjust quickly? And critically, is the effect of the shock permanent or temporary? For instance, the graphs here illustrate accumulated responses. Consider the scenario in the highlighted box. A shock to money supply, M1, leads to GDP increasing and staying permanently higher, as depicted in the top left graph, where the response curve settles at a new, elevated level. This slide provides a quick EViews syntax cheat sheet for estimating vector error correction models. First, we estimate an underlying VAR model in levels, like var v1.less14 GDP M1 TB3, to determine the optimal lag length. Here, v1.less indicates a standard var, and 14 specifies a lag range from 1 to 4 for the variables GDP, M1, and TB3. Once the optimal lag is selected, we perform the Johansson cointegration test using a command such as v1.coint(s), 3. The (s), 3 argument means we want a summary output and are applying the test under case 3, which assumes an intercept in the cointegrating equation but no trend in the data. After confirming cointegration and its rank, we estimate the VECM itself. The command var vecm1.ec, c, 1, 14 GDP M1 TB3 is used. This is where our pro tip comes in. The .ec command suffix is crucial as it triggers the VECM estimation mode within the var object. The c, 1 argument specifies that we are including a constant term in the cointegrating equation and that we found a cointegration rank of 1. The 14 in this context refers to the lags of the differenced variables in the VECM, meaning a lag order of 1 to 4 for the difference terms. Finally, to analyze the dynamic responses of the variables to shocks, we generate impulse response functions using vecm1.impulse. This command will output the graphical representations of how each variable responds over time to a shock in another variable within the VECM system. We conclude our presentation with a final thought on data and modeling. Data speaks only when you ask the right questions using the right models. I also want to acknowledge the key resources that informed this presentation: EViews 13 User's Guide to, S&P Global,